Welcome to qnawire.
So first, let's write down the known informations. So we know the mass of each bag, let's call that MB, and that's given to be 10 to the power minus 3 kgs. And we also know the gravitational constant, that's equal to 6.67 times 10 to the power minus 11 Newton times meter square over kg square. And this gravitational constant we are going to use this further in this problem, and we are uh, given that one bag is at the north pole of earth and the other one is at the south pole, so we can find the distance between the two bags, and that will be equal to twice of the radius of the earth, where the radius of the earth is 6 6.371 times 10 to the power 6 meter. So that's the radius of the earth. So using that we can find the distance between the two bags. Now in the first part we have to find the number of protons in each bag. So we know that MP, the mass of the proton, is equal to 1.67 times 10 to the power minus 27 kg. So this is the mass of one single proton. Therefore, Mv will be equal to number of protons inside each bag times mass of the proton. So from here we can find N, which will be equal to Mv, the mass of each bag over mass of each proton, and that will give us 6 times 10 to the power 23 after substituting the values. So this is the number of protons in each bag. So that's the first part. Now in the second part, we have to find the electric force and gravitational force. So the electric force is given by 1 over 4 pi epsilon naught square of, like, multiplication of all the charges of both the charges of the two bags over square of the distance between them, that is d. And here, since both the charges are equal, so because they have the same number of protons, so this will then be equal to q square, where q is the amount of charge in each bag, over d square. And let's write this factor 1 over 4 pi epsilon naught as k. So this is equal to kq square over d square. So we need to find q here, because q is not a charge on a single proton. This will be actually equal to total number of protons inside each bag times charge on a single proton. And this is actually equal to magnitude of a charge, magnitude of the charge in an electron. So we already found n in the first part, and we know the charge on a single proton, or the magnitude of charge in a single electron. So we are going to substitute that as well. That is 1.6 times 10 to the power minus 19 coulomb. And this gives the total charge in each bag. So now that we have Q, we just need to find D, the distance between the two bags, and that, as I wrote over here in the known information, so that is equal to twice of the radius of Earth, and substituting the value for RE, we get D to be equal to 1.3 times 10 to the power 7 meter. And K, which is 1 over 4 pi epsilon naught, is actually 9 times 10 to the power 9 Newton meter square per coulomb square. So substituting all these three in this equation, let's call this equation 1, we can find Fe, which is the electric force. So Fe comes out to be K times Q square. Oops. Okay, so I think I messed up over here. This is actually, I swapped the two numbers. So this should be equal to 9.6. Yeah. So here we have 9.6 times 10 to the power 4 coulomb, and square of that over d square, that is 1.3 times 10 to the power 7 meter per square. And solving this, we get the electric force to be 4.9 times 10 to the power 5 newtons. So that's the electric force. And then we need to find the force of gravitational attraction, or the gravitational force, and that is given by G, which is gravitational constant, m1 m2 over d square, where d is the distance between the two bags. And this is equal to, so we substitute each of the values, and we already know mass of the bag, that is mb, so this will be equal to gmb whole square, because both the masses are equal, over d square. So now substituting the values, we get Fg to be 3.9 times 10 to the power minus 31 newtons. Now your values may be slightly different from mine, depending on how accurately how accurate your calculations are. For example, K is exactly nearly equal to 8.99, but I have approximated that to taking 9 over here. So yeah, it will be very slightly different, but the order of the answers should be same. Should exactly be same. Okay. So now for part C, we basically have to see whether the forces are large enough for us to feel that if we are holding one of the bags. So as if you compare these two, you'll see that Fe is actually very large and Fg is very small, which means that the electric force between the two bags is very large, and the gravitational force is very small. So it's not that both the forces are very large, one of them is large and one of them is small, but the net force will be sum of these two forces. So uh, you will feel that you are holding one of the bags, because the net force will be positive and will not that be small. So yes, we see that the electric repulsion is large compared to the gravitational attraction, so we should hold the bag. We should feel like we are holding the bag.